Yes. So first of all, I want to say those of you who got up this morning after partying till midnight last night represent the best of the best. You will do well in life. All things are yours. And I'm very impressed. Okay. Next, I really have two objectives for today. The first is to prove this. Well, it was theorem 1.3. You know, it's this fact that when I take this quantum surface, so we had a field H and an independent SLE eta, and I told you I have a definition of quantum length along the path because I can unzip and measure the length down here, and that gives me a notion of length when I zip back up. And the statement is that if I take a piece of length on this side, you know, I map back and measure how long it is. And I take a piece of quantum measure on this side, and I map back and measure how long it is. Then these two things should be the same. Okay. So that and that justifies our saying that this curve is what we call a conformal welding of these two quantum surfaces. We glue them together according to the length parameter on the boundary, and then conformally map. Okay, so that's topic number one. Topic number two is open problems. And so, as everyone knows, you know, you're not being paid to come to this conference just for your own benefit. The hope is that you will actually produce something. You know, so. And this is a field where there are a huge number of very fundamental open problems. So I'm going to give you those. I have a long list. And I thought maybe I would actually start with the problems and maybe try to do half hour or so, maybe about half the time doing open problems, and then go back and do the proof. Now, you know, when people give open problems to students, there's sometimes two directions they go. Sometimes they might give you a problem that they don't care that much about, but they think it's something that you can do. And as a good warm-up for learning the subject, you know, you don't necessarily have to tackle the hardest problem first. You want something to get started, and so they give you a solvable problem. The other thing they might do is give you the problem that they care about passionately and have been sort of banging around in their mind for years, and they would be just so grateful if anyone could solve it, but it might be extremely difficult. So out of respect for you, I've chosen mostly questions of the latter type. But you know, I'm still optimistic that some progress can be made. So I have a very long list of questions, and all right, so let's skip ahead to that. Okay, so first, in order to formulate the questions, I want to give you a couple first of definitions, and some of these will be fleshed out a little more in a forthcoming work with Bertrand. But so we talked about quantum wedges as being the kind of very natural notion of a random surface with infinite area. So I'm not sure if we exactly use that term, but just whenever you take a Gaussian free field and then you add a log, that's equivalent to taking so a centered Gaussian free field and add a log, which is equivalent to taking an infinite wedge with a zero bound, with a centered Gaussian free field, because then when you conformally map by z to the alpha, and you add the log of the derivative, that's a constant. You know, q times the log of the derivative is then, well, it's a constant times the log of z. So, so we have this, and that's what we've been zipping up. We've been zipping up to infinite area, infinite boundary length random surfaces. But you might ask, what is sort of the most natural random surface with area 1? You know, you might want a sphere of area 1, or a disk of area 1, or a disk of length 1. And so I just want to say there's one pretty obvious thing you can do. And that's the following. Let's say I take a domain D, and I fix some function h naught on the boundary. Maybe I'll take it to be 0 on the boundary. And well, okay, let's see. Let me go to the other board. I want more room. And so I'm going to give you two different things I can do. In one case, I'll take a domain with 0 boundary conditions here, and I'll take a free boundary section. I take the Gaussian field with 0 boundary conditions here and free boundary on this line. Okay, if you'd like to think about it, take 0 boundary conditions on the whole thing, then take even and odd parts. And the odd part will give you something with 0 boundary conditions here, and the even part will give you something symmetric. And if you restrict to this half, it's free boundary. Okay, so I give you that object, and then the other. And here's what I'll do. I'm going to condition on mu sub h of the domain being large. C is large. I'm going to take C to infinity. And okay, what happens when I take this and I condition to be large? Well, you know, if you look at this paper with Bertrand, it's not very hard to see what is the easiest way for a surface to become large. The easiest way for a surface to become large is just for it to get big at one point. H is really big at one point. Right? If H were going to be really big here and really big over here, that would be, you know, overpaying, because you could just, you know, if you just want to make it twice as big, you could just lift up H a little bit here, and that would make it twice as big. So what will happen is that as C gets large, most of your mass is will be concentrated near a particular point. So when I condition C to be large, I'll get lots of mass near a particular point. Okay, so now what I want to do is take the limit as C goes to infinity. So I can normalize this measure. I'll define mu hat to be mu h divided by C. So this mu hat has total area 1. So basically I condition the total area to be C, and then I divide by C, so the total area is 1. Okay, and I claim that that converges to a limit. And that this limit is going to be what I will call a quantum disk. And what's the limit? How can you understand the limit? Well, one way to understand a limit is to say, take this surface and choose 2 points uniformly on the boundary, and take 1 point up here, and then conformally map to the half plane so that these 3 points go to 0, 1, and this point up here gets mapped to infinity. And when you do this conformal map, you'll see, because when C is large, these points are probably close together, because all your quantum mass is concentrated locally, then what will happen is that this piece of the boundary will be very far away. As c gets large, this piece will get further away, closer to infinity. And you can show that, in fact, these mu h's converge to to sort of a limiting. So for each c, you get a random unit measure on the plane, on h this way. And you can check. It's not that hard that as c goes to infinity, this is converging to a random unit measure on the plane. And that this piece, these things are getting closer and closer together, so this piece you don't see in the limit. Okay. And there's a similar thing you could do with if you wanted to create a quantum sphere, then I can just say I condition the area to be D. But now I take zero boundary conditions everywhere. And in this case, if I pick two typical points, instead of having all my mass be up here near the boundary, I'll have all my mass be near some location in the inside. So now if I can formally map this to a sphere where I make these 2 points go to, say, -1 and 1, then, and the sphere is centered at 0, well, requiring the sphere to be centered at 0 and these points going to -1 and 1, that determines the radius of the sphere. And as c gets large, these points will be closer and closer together, which means the radius of the sphere will be getting bigger and bigger. But I still expect to converge to a random measure on the sphere. Again, sort of, I have 3 on all of C. Okay, so and you can give simpler, you can give other constructions, more explicit constructions of this limit. But I guess if you didn't follow all of that, my point is simply that there is a natural notion of a quantum sphere and a natural notion of a quantum disk. Okay, and these things will be in the conjectures. So, okay, so what do I want people to prove? Yes?
So you have your H with 3 boundary conditions on one and so you can decompose it into some contribution coming from a Gaussian field with some contribution coming from so how do you know from the line? So how do you know that
Well,
when you condition not everything is actually going to be one from the line and then you just get some power later?
in which case? In the one on the left? So how do I know that what doesn't happen?
Well, I mean, as you say, all the mass goes to the boundary.
Yes.
So that locally you just see something on the boundary for some like extent, and then there's the fluctuation path inside of it.
Well, oh, you mean that, so you're afraid that there's no quantum mass in the interior? That you're afraid that this function becomes harmonic? I mean, look, if you condition on the boundary, the inside is always the Gaussian free field with that boundary. Always the same variance, because I'm just taking quantum transformations. I'm not doing anything that would change the variance.
So my question is, you know that when you let condition on the large mass that C goes to 0,
Uh-huh.
that it's not the boundary guy that's
Well, I mean, in this case, Okay. I mean, there is a little bit of work to do to check these limits exist. I haven't quite done everything for you. But essentially, what's happening? So maybe say a little more. What I think of is, I'm sort of forcing this orange thing to be very long. There's another variant of this where I just condition the length of this thing to be C instead of the inside area to be C. And then I get something with unit length on the boundary. But either way, if the length is long, the area will be long, typically. If the length is big, the area will be long, and vice versa. So but the point is you can really check to see what happens in this case. So if I were to let's say I choose a special point from this. I choose a point, and then I map that point to 0. Okay, so now I've taken my measure weighted by a special point. So I take the measure, I weight by the total measure, and choose a special point from that measure. So I get a marked measure. And now I take that marked measure, and I want to condition the total area to be large. So I've got 0 boundary conditions here. I've got this orange here. And I want to condition the total area to large. Well, if I just look at h sub epsilon, if I weren't doing any conditioning, that would be a Brownian motion with some drift. And it means that, if I look at sort of the area of successive logarithmic annuli, when the Brownian motion is drifting, what will happen is that the expected areas in these successive annuli, each one being half, will be kind of drifting downward. So I have these areas drifting downward. Now, if I condition the area to be large, what will happen is that instead of these, so these are the log of the areas. So instead of these areas tending exponentially smaller, as these things get smaller, what will happen is they'll go bigger for a while and then get exponentially smaller. So you can show that the easiest way for this thing to be big is for it to just kind of march up, get big, and then march down. And if you were to actually parameterize time by the area, then you would get a Bessel excursion. But you're leading me down a path I wasn't intending to go down. It's more detail than I was intending to give. But yeah, essentially, you can give, using Bessel excursions, you can give a very explicit version of this construction and see exactly what everything is. A key fact is just you really know what things look like near a typical point. And then when you condition the area to be big, you can see what has to happen. You have to get big and then small. And the time at which you reach big will be further and further away from the origin in this model, which means that I've got an origin here. The place where I get the next big annulus, the biggest of these successive annuli, will still be a very small one. It would be similar if I measured in terms of length. And then once you actually have this function, either the boundary version of the function where you look at the lengths of these successive guys, or the area version of the function Once you have one function, you can just go and get the other. So if I condition on the boundary lengths, then I kind of know what the field is doing, and I can then sample the area and see roughly what that's doing, and that it's following a similar trajectory, and vice versa. So then you kind of see that, if the boundary lengths, roughly speaking, the area of this should be the square of the boundary length of this, and when you graph the logs of each of them and convert that into information about H, you can see that that's indeed the case. I don't know. Does that answer it? Okay. Okay, so here's some questions. So first of all, I would like to know that if I take the uniform quadrangulation of a sphere with n quadrilaterals, then that scales to the unit area quantum disk. This should hold in the metric of weak convergence of area measures with gamma equals 8/3. Okay, it's not so hard, right? Just, and you can, in order to embed it in this, I give you the uniform quadrangulation, you pick 3 points uniformly from it at random, conformally mapped, so those 3 points go to -1, 1, and infinity. Look at the area measure you get on the complex plane. It should be the same as this area measure. The same law. Okay, this is a very explicit conjecture. Okay, so prove that. And subsequently, there are versions of this where you look at a disk. Say you take the uniform quadrangulation of a disk with boundary length n, and you weight by a critical constant to the area. So the area is random, but sort of weighted in a critical way, and the length is fixed. Then this should go to the unit length version of the quantum disk. And then the version of the quantum disk where the area is fixed and the length is random, you should get similarly by putting some critical weight on the length. Okay, so these are, 3 simple conjectures about, and I don't know which one of them is easiest to start with. Probably if you can do one of them, you can do all of them. But somehow, uniform quadrangulation and spheres on a disk, it should be converging to something. It's also, earlier in this paper with Bertrand, we talked about if you take an infinite volume limit, so you just zero in your 1 point, you should get one of these quantum wedges. But here's a finite version of the conjecture. And the same thing should hold if you take random quadrangulations weighted by the number of Ising configurations or ON configurations, all these statistical physics models, uniform spanning trees. And in that case, the cluster boundary loops should scale to a CLE kappa that's independent of the measure, with gamma equal to the square root of kappa. Okay, so this is all scaling limit stuff. Prove discrete things have Liouville as a scaling limit. Another thing I'd like to know, this is that footnote I showed you a couple times ago, is that a quantum surface is a coordinate change invariant metric space. Yes? Well, it's because it's this conformal ansatz that once you condition on the metric, I mean, in any one of these cases, if I condition on the graph, conditioned on that, I just have this statistical physical model on that graph. So if I choose a random graph where the probability of a graph is proportional to the Ising model partition function on that graph, and then given that graph, I choose the Ising model partition, I choose an Ising model from it, then I get is, condition on the graph, condition on the embedding conformal map from that to the sphere, then it should be that that these models are conformal loop ensembles on this sphere. This is essentially that picture I showed. Yes, so this is the heuristic here. if I take this graph and conformally map it here, and then I resample this arc, I resample the whole tree structure, I fix the graph and then resample the tree structure, the tree should be an SLE. So it's an SLE on a random graph. I mean, it's a loop-based random walk on a random graph. But even on a random graph, it should be that simple random walk approximates Brownian motion on the manifold. And because of that, loop-based random walk should approximate what would be the SLE on the manifold. And so that's the reason. So you conformally map it here. This should be, even after you fix the graph structure, which determines the metric, even conditioned on that, this should still be an SLE, which in particular implies this is an SLE independently of the measure. And sort of an ansatz is that that should be true for other models also, not just for loop-based random walk. That's right. No, and it wouldn't here. I mean, think about it. If I take this triangle and I divide it into a million smaller triangles, then this should still look like an SLE. There's just a, it's wiggling a little faster here, but still in the limit it should be an SLE. So somehow, if I have a lot more area here and a lot less area here, the shape of the path shouldn't care. Yeah, that's right. But of course, that's not proved. I mean, even the fact that simple random walk on this graph looks like Brownian motion on the manifold, that's already out of reach. Okay, so so number 2, quantum surface is a coordinate change invariant metric space. This is what I said last time. You can, if I give you a quantum surface, you can say, how many delta balls do I need to connect? How many Euclidean balls of quantum size delta do I need to connect one point to another? And as delta goes to 0, this should be scaling like some power of delta. And if you divide by that power of delta, it should be converging to a limit, which is just the distance. But we don't know that. But once we know that, you might want to show that all of the above scaling limits also hold in the topology of Gromov-Hausdorff convergence of metric spaces. Okay. So So I've now given you 3 very challenging and fundamental open problems. Now, of course, in reality, when one gets started, one will start with easier problems and just try to chip away bit by bit. So a more modest thing you might suggest is first just show that a simple random walk on a random quadrangulated surface is a good approximation for Brownian motion on that surface. Okay, this kind of already gets you to some sort of statement, but it doesn't give you the convergence of metrics. But and I would say, well, prove any SLE convergence result at all about random planar maps. All the SLE convergence results we know are on deterministic lattices, but it was always believed in physics that somehow random maps were easier to deal with than deterministic maps. And in many cases, combinatorially, for many purposes, they really are easier. But partly because we can't do this, we haven't figured out a way to do this. So anything, or any partial result, or any any understanding one can give at all about random walks on these surfaces, what they do, how far they get from the origin, anything is already nice. Okay. Now, another question is, if it turns out that the quantum surface is a well-defined metric space, what does the boundary of a unit ball look like? I might think that if I take a quantum surface here, and I fix a point, and I look at all the things that are distance 1 or less from that point. So I get some randomly shaped ball. But not only that, there may be things inside here. There may be a little hole here because it may be there are points in here that are further from 1. Because there could be a big mushroom or something. H could get really big here. So it may be that I can get to all these points around here faster than I can get to points in this little hole. So the boundary of a unit ball will not be connected necessarily. But I should get some object. If I have an Rm symmetric space, I should get some curve with some collection of smaller curves inside it. So conjecture for me anything reasonable about this collection of curves. Give me a heuristic argument for something. Is this a kind of SLE? Does the outside look like the inside? Can you say it's the fractal dimension of this boundary? Can you say how close these holes are to the boundary? Is there a big how big is the region in the middle where you don't have holes? Just give me anything to work with here, where you can give me a plausible argument, a plausible heuristic, and just not even asking for a proof. Give me some reason to think I have a guess for something in this about these shapes, because as it is, we know nothing. And we have all these wonderful tools of conformal invariance and all, these coordinate changes, everything we can work with. This shape will be invariant under coordinate changes of the map. So we have all kinds of things to work with, but and you might think you could be able to give some sort of a guess for what this process should be in terms of conformal weldings or some other nonsense. But, okay. In the discrete case, I also don't have anything. Well, okay, when I say anything, it is true that there are some things that are known in the Schaefer, via the Schaefer bijection. So, so the structure of this is a metric space. In this special case, gamma is the square root of 8/3. So they take the scaling limit of this and they call it the Brownian map. They don't, assuming it exists right now, they just have proofs that subsequential scaling limits exist. So they know some things, but nothing that would tell us anything about the shapes of these guys, because they don't know how to put a conformal structure on it. They don't know what random walk looks like, Brownian motion looks like. So, so they can give you some things about distances. I mean, what can they do? There are 100 papers on this subject. They clearly know something, but I think it's safe to say nothing at all about what happens when you look at the conformal structure. Okay, but another question. So getting back to their structure, you could ask, what should be the continuum random tree analog of the breadth first search tree, as in the Schaefer bijection? So the Schaefer bijection, remember, you have a random graph, and essentially, in all these variants, there are lots of variants of this bijection, you essentially construct your random graph out of two trees. You have a tree and some sort of a dual tree. So it's always you sort of have a pair of trees that you then glue together to construct your surface. And so you might think, well, if I took the scaling limit with the conformal embedding, I would get a pair of trees over here. If I get some surface with some continuum space-filling tree, maybe like the scaling limit of a uniform spanning tree or something, and some other continuum space-filling dual tree. Okay. I don't know if this looks like a pair of trees, but that's the idea. So these are interwoven, both space-filling. So this the point is the paths don't cross each other. So you ask, what's the scaling limit of these trees? When you look at their conformal embeddings, what do they look like? I mean, we know an awful lot about these trees. We know if you break things apart along one branch of the tree, then you have some independence of the left side and the right side. So you're conformally welding two things together that are independent. We know about the structure, how long these things are. I mean, like I say, there's a lot of stuff you can get combinatorially about this Schaefer bijection tree. Could you take these things, this independence of one side of an arc and whatever other properties you have, and convert it into something about the continuum that would give you enough information to tease out a conjecture of what this tree looks like in the continuum? It would be very nice. I mean, let me say in this model too, if I look at the boundary of a unit ball, and I fix the unit ball and condition on the length, what goes on outside is completely independent. If I condition on the area of what's inside, then so essentially I'm gluing together two independent surfaces here, one on the inside, one on the outside. They don't have the same law, these two surfaces, but whatever this shape is, it's the welding of independent things. So a general understanding of what happens when you weld together two independent quantum surfaces is interesting. In this particular case, if you look at the outer boundary, the outer surface is just going to look like a Louisville quantum gravity surface. Should be. I'm conditioning on the length, and so then the ball is fixed, and then the outside has complete freedom. This should just be a free boundary conditions Louisville quantum surface. So I'm going free boundary quantum gravity to something, to whatever this mysterious unit ball looks like as a metric. And what do we know now? Well, we know how to glue one Louisville quantum gravity surface to another Louisville quantum gravity surface. Thanks to this work by Peter Jones and Astala and co., we know how to glue a Louisville quantum surface to a disk, to a unit disk, and at least show you get a curve. Now I'm saying glue a unit gravity Louisville quantum surface to something mysterious, this unit ball, and show me what the curve looks like. Okay. So, there's hope that with the right amount of cleverness, someone, I think, could, use all these conditional independence properties, Markov properties, all these things you have at your disposal in the discrete model to cook up a conjecture. And just like SLE was cooked up as the right conjecture before anything was proved to converge to it. Louisville quantum gravity, these zippers we're doing, these are cooked up as conjectures based on principles that the scaling limit should satisfy. So, okay. Good luck with this. I mean, I'm not convinced it's completely hopeless. Another way you could formulate this problem also is to just look at the outside and start taking slightly larger balls. So this is a ball of radius 1. Let's look at the ball of radius 1 plus epsilon and 1 plus 2 epsilon. And what you'll find is as you add these strips, I have a random surface. When I add a strip, it might be that when I add, if I conformally map the ball to a sphere, and then I add another strip, then it might be I find that I add a quadrilateral here that connects to something over here. So I'll get a pinching. So if I take a sequence, here's the ball of radius 1. Here's the ball of radius 1 plus epsilon. Ball of radius 1 plus 2 epsilon at 0. And at each step, I conformally map the whole thing into a circle, setting 0 to the origin. I might expect there will be some sort of a time evolution in which what happens is when I go from here to here, I shrink everything a little bit, but I also have the possibility of pinching some things off. So I'm sort of folding in new loops. So when so if there happened to be that when I observe the ring of epsilon, this point gets connected to this point, then it might be that this whole section here becomes part of a loop here, what you might call a sort of a pinned loop, if you will. And as I keep doing this, I'll get more and more kind of pinned loops appearing at uniformly random points along the boundary. And OK, so you might wonder, in the fine mesh limit, what's happening? We should have some continuum model for folding in little random loops. And so I'm looking at Vindelen. There's something like this in the paper that we just put on, 2 papers we just put on the archive about conformal loop ensembles, and understanding them and how they exist, and various characterizations of them. But I'm not convinced that that's exactly what these things are, but it's a question. And on the discrete level, we know exactly what's going on. I mean, on the discrete level, you have a surface, and each time you add the next boundary level is completely independent. It only depends on the length of the outside. It doesn't care about anything that's inside. And so I just look at all the things I can reach from here in one more step. And you can sort of work out with combinatorial tools what the law is of what's going on. And when you look at these, the things that get pinched off, how often they appear. And there are a lot of combinatorial tools at one's disposal. OK. So that's that. So really understand, at least conjecturally, what these trees, unit balls, that whole story looks like in this conformal gauge. OK, next question is, can you take a kappa equals between 4 and 8 version of the quantum zipper to prove the time reversal symmetry of SLE for kappa between 4 and 8? OK, so how does this work? So probably it has not escaped your notice that this welding fact about quantum gravity does give you an independent proof of time reversal symmetry when kappa is less than or equal to 4. So there's been a proof by Dapeng Zhan, and I guess Julian has a. Is that right? Do you have an independent proof of? No, it's not a proof case. Sorry, he has a different proof of duality, right? So there has been a proof by Dapeng Zhan of this, and it. But this gives you a completely independent one because when you glue together quantum surfaces that they you know, I'm gluing together something here that's independent of something here, and these two things have time reversal symmetry. The Gaussian free field has time reversal symmetry. And it's a fact that for proving the time reversal of SLE, it's enough to do it sort of near one typical point. I mean, I guess let me say, if you could show the time reversal is absolutely continuous with respect to the forward path, then that shows that the whole thing must be reversible. So you have a anyway, you get that from this. Okay. Now, okay. So what would we want to do in the kappa bigger than 4 case? Well, in that case, what happens? You have a path that hits itself and the boundary. And if you look at the right side of the path is not going to be a connected set. It will be a sort of tree of little sausages. And the left side will be sort of an interwoven chain of, or tree of sausages. So, you know, if you did this on a discrete case, sorry, this should be pink, same color. If you did this on a discrete lattice, then these, you know, if you took like an SLE6, you'd have a well-defined left side and a right side. It's just that the left side would be kind of pinched at various points. And the right side here is also going to be pinched at various points. And so in the scaling limit, you get sort of they say kind of a tree of little sausages linked together, and a tree of sausages on this side. Okay, so this is, so I'm doing some work with Bertrand, which is just constructing a tree of sausages. So we're producing the sausage tree. But if you like, this is one way of constructing the tree of sausages. You just draw the SLE cap, and you look at the two sides. And now the question is, what happens when I start to unzip? Well, when you unzip, when I conformally map back, what you'll see is that I'm basically taking SLE up to some stopping time. I take SLE to some time, and I map the complement of that SLE back. But because the curve is space filling, this whole positive area of the space is not in the domain of the conformal map. So the way I think of it is, all this stuff up here is getting mapped to the plane. So everything above this line is getting mapped to the plane. And the stuff below this line is getting mapped to, I'll just kind of draw it down here as sausages hanging off the side of this. Maybe I can draw each piece of the sausage as a unit disk or something, and they're all kind of hanging off down here. So now, if you like, I have this tree of sausages here, a tree of sausages here, and when I zip up, I should have a boundary length on the outer perimeter of the tree of sausages, a boundary length on the outer perimeter of this tree of sausages, and I should zip up sausage trees according to tree boundary length, find that they magically interweave in this funny way that gives me this SSLE. Okay, I don't know how to do that, make sense of that. But I'm also not convinced it's impossible. And if you could do this, and you could check that the laws of these pieces are kind of independent, then you would have an argument for time reversal symmetry. Because, you know, I take one of these guys, another independent one, I glue them together automatically, that gives me something time reversible. So, okay. So that's the question. Understand the quantum zipper in the case kappa between 4 and 8. Okay, and next question. Oh, and I should say, if you wanted to actually get the proof of this, then it would require showing, when I take this conformal map from here to here, when I map back up this way, I would like to show that there's a unique way of doing this zipping up, which would require showing that this SLE curve is what we call removable in the conformal, in the complex analysis sense. That there's no continuous homeomorphism of this, no non-trivial continuous homeomorphism of this half plane, looking like the identity near infinity, that is conformal off of this curve. So somehow it's rigid. This curve is sort of fixed by the conformal structure. So that's something that, unfortunately, this result by Stas and Jones, Smirnov and Jones, it only works for kappa less than 4. So it doesn't yet deal with this case. So another question, if you have a hankering to do some analysis, is just prove that SLE is removable. SLE kappa is removable when kappa is between 4 and 8. Okay. Next 3. What is the Hausdorff dimension of a quantum surface, assuming it's defined as a metric space for general gamma? So we know that it's 4 for this Brownian map, or what should be gamma equal square root of 8/3. Generally, can you give me a guess? But there's no guess in the physics literature that Bertrand or I is aware of. So give me a guess. You know, heuristic, anything. Tell me, does it tend to 0 or 1? You know, how does it, as a function of gamma, is it continuous? Is it anything at all? Yes? The gamma should be square root of 8/3? Well, you know, if you go back to this whole picture, if you look at pictures like this one, no, not this one, no, up here, this thing with the trees, if you look at this picture, we know that if you take 2 independent surfaces, we don't have trees here. If I just take 2 independent surfaces and glue them together, I can arrange so that the interface between them is a self-avoiding walk. So if you believe the self-avoiding walk is SLE 8/3, then you know that when you glue together 2 of the surfaces corresponding to the scaling limit of this uniform quadrangulation, then the interface between them should be an SLE 8/3. And that only works if you take gamma to be the square root of 8/3. So I think that's the quickest way to see it. Today, of course, in the physics literature, there's a tremendous, you know, this is related to central charges and conformal field theories, and they have many ways of seeing this. But this is the one that's sort of clearest to me. Okay. So the next question, let's see. Yes, so Hausdorff dimension. Really say anything at all about the metric space structure. We don't even know it's a metric space for now, but you can take a small delta and define it as a metric space the way I said, and you can ask about this behavior for small delta. So even if you can't prove a limit exists, you can prove sort of scaling properties. Maybe you can say something about these approximations. So anything at all one can say about the metric space structure. I really mean anything. Just find some statement that one can prove. That's already a paper and something new, because we don't know anything. Except when kappa is, when gamma is the square root of 8/3, there are all these things we know on the discrete level, but even then we don't know anything on the continuum Liouville quantum gravity side. Okay. Next question is, if I take the h sub epsilon, h superscript epsilon, to be smooth mollifications or piecewise linear projections of a Gaussian free field H, do the flow lines of e to the I h over chi converge in law to SLE curves? These SLE AC geometry flow lines as epsilon tends to 0. So in this new work with Oded Schramm, we show if you take this random triangulation, look at its piecewise linear, you project your Gaussian free field onto the space of functions that are linear on a lattice triangulation, and you look at the level sets of that. Those are looking like SLE4. But we don't have any result about the flow lines of e to the IH over chi, which should be the other SLEs. The problem is find some. You can take whatever kind of, you can approximate it by a lattice, you can replace H with its average on a circle, or you can mollify it against a bump function supported on a small region so that you get a random smooth function. Or take any approximation of the free field you like that's a continuous approximation, take the flow lines of that and show they converge to SLE in the limit. So we don't have that. And on the Liouville gravity side, similarly, if I take smooth mollifications of the free boundary Gaussian free field, then I just get some random continuous measures on the boundary. E to the gamma h epsilon will be some smooth function on the boundary, and so I just get some measure that's actually absolutely continuous with respect to Lebesgue measure. Its radon-Nicodemus derivative is smooth. And now I glue that together, and one would think I would get some sort of a smooth approximation of SLE. But here's the tricky thing. Knowing that the measures converge doesn't tell me that when I zip up, the path converges to SLE. And here's the region. If you haven't seen this before, this will blow your mind. Well, at least it blew my mind when I first learned about it. So I don't know who first discovered this counterexample, but it's a pretty standard thing in the conformal welding world. Let's say I take this line and I unzip and I look at the homeomorphism I get on this corresponding R, this homeomorphism between the left side and the right side. So when I unzip, I'll find that because this is a straight line, I have complete symmetry. So when I unzip, this point goes here maybe, and to here, and I get simply the map x goes to minus x, mapping from one side to the other. Okay? So it's very simple. Now over here, let's say I take this as my map. Okay. Now you can kind of see that if I, if instead of taking this, if I just took a triangle, the whole triangle, and unzip, then I would have complete symmetry. And this piece on the triangle would get mapped to minus what this piece of the triangle got mapped to. But that's going to be approximately the case here, because this looks approximately like that triangle from the conformal point of view. So when I draw the map here, it's going to be approximately the identity map. So I have something that's approximately the x, minus x to x map. And yet, when I zip up, I get something that's completely wild. Okay, so this tells you that knowing that these two functions are close on the boundary in the sense of L infinity norm does not tell you that when you zip up, you get the same thing. So, what it really tells you is that, L infinity is just the wrong topology if you really want to say that two homeomorphisms are close. And it's not really clear what the right topology is. The complex analysis world, has not yet worked out a very complete understanding of what weldings, what homeomorphisms correspond to what kind of curves. We only just know that you can make really small changes and mess everything up. This is almost space filling. Okay. But you still might wonder if this is, I know that if I take this quantum measure here and zip up, I get SLE. If I take a smooth mollification of the measure, maybe I still get something close to SLE because, maybe in order to get something this contrived, everything has to conspire just exactly the right way. And maybe that doesn't happen when you just smooth out and you have all the randomness. So it's not unthinkable to think that this could be true, despite pathological examples like this. Okay, next question is, what happens when gamma equals 2? So kappa is equal to 4. So in that case, my definition of quantum surface makes perfect sense. If I, so remember how I defined quantum surface? I had this Q equals gamma over 2 plus 2 over gamma, and I had this map, dH going to d tilde h tilde, and I defined h tilde by adding q times the log of the derivative to h, to the composition of the conformal map with h. And I said that, it's an equivalence class of pairs under this transformation. Okay, that definition makes perfect sense when q is any number, in particular when q is this number. On the other hand, for this value of q, we do not have a way to construct a random measure. So this object, this thing where we take limit as epsilon goes to 0, as of epsilon to the gamma squared over 2, e to the gamma h epsilon of z dz, and we construct a random measure in the limit. Epsilon goes to 0, yes. Thank you. This random measure converges to 0 almost surely if you take gamma equal to 2. On the other hand, maybe if you normalize in some other way, you can make it converge to something. So it converges to 0 almost surely, but maybe that's just because this is the wrong factor. Maybe you need to put in some log or some other business. And maybe there's some way to make sense of this limiting measure. And we just haven't figured it out. But that's, right now we just don't understand anything about gamma equals 2. Even though it's right on the border and it seems there should be something. Yes? Well, see, it's not really so clear. We know that when the measure is bigger than 2, that seems to be what happens. But we really, I mean, what we know is that if you look at the support of this measure, it's a random fractal set, and the dimension of that fractal set goes to 0 as gamma approaches 2. And so what's a 0 measure random set? Well, you might think it's a point. But we don't really have a good proof that it's a point. I mean, so maybe this measure converges to a point mass if you normalize it correctly. But we don't even know that. Well, that I also don't know. You could try that, varying gamma and epsilon together. Maybe that would give you an interesting limit. I don't know. I mean, that's a nice idea. If you want to construct something meaningful in the 2 case, maybe you can do that. I will tell you that based on what you know, the discrete models, they think that as gamma approaches 2, these random surfaces approach the boundary of the continuum random tree. So imagine I take this continuum random tree, and I construct this by gluing together some actual, maybe I take some sticks, and I glue together physical sticks to make a physical rendering of this tree. So now I have an object. All these sticks are maybe epsilon in diameter. So I get some physical 3-dimensional object, which is small diameter things. And if I look at the outer boundary of that surface, that's now a random surface. But if I can formally map that random surface back to the disk, and I take the outer boundary of this, I look at the bottom of this point, I take the boundary of that to be the boundary of what I map to the disk, then I'll find that most of this stuff gets mapped to kind of one point. But still, this tree is there. And if that tree is a random metric space, you might wonder, can you make sense of, is there some way when gamma is equal to 2, you can make sense of Louisville quantum gravity as a random metric space? Or at least can you show in some limiting sense how this tree appears as gamma approaches 2? The gamma 2 is clearly interesting. Continuum random tree is interesting. In the physics world, it's interesting. But we just don't understand what to do with it. So right now, it's sort of being ignored. But I think it's sort of unfair. It deserves to be looked at. And another question is, what happens to our coupling theorem? Theorem 1.2, this zipping up question. So this invariance under zipping, if I take this definition of quantum surface, just a pair of things invariant under this, then this theorem 1.2 tells me that when I take this structure, I take this quantum surface with this independent SLE on it, then it is invariant under unzipping. So it is stationary with respect to that, even when gamma is equal to 2. But what's not clear is whether there is a canonical way to rezip. Because I don't have a notion of length here or a notion of length here. So I can't say, well, it's just the welding of the length measure. And so I don't have that piece that tells me it's a welding. I also don't have the piece that tells me that this curve is removable. Because we don't know whether, so the Jones-Smirnov result doesn't work in this case. The cap equals 4. So we do not know whether SLE4 is removable. Just like with all the SLEs bigger than 4. So we're hopeless. but maybe not. Maybe it's still the case that the curve is determined by the field. You know, it's an interesting puzzle. Why is it? Is it determined by the field or not? I mean, you know, giving you a question, it's binary, and I can see either of them being plausible, so I don't really have a good guess for which of the two. Okay, next question is, could you understand a simple random walk on a random quadrangulation in terms of the Schaefer bijection, or this Moulin bijection where it's something, if you've ever seen me give my hamburger cheeseburger talk, it's the bijection you start with there. But it's something where you just take two uniform random trees independent of each other and glue those together. And you get, instead of pure quantum gravity, you get a quantum gravity with a uniform spanning tree on it. But in any of these models where you glue together two random trees, can you understand simple random walk in terms of these trees? You know, I give you the pair of trees. I have a very nice mathematical description of them. The simple random walk is somehow jumping around these trees. You know, if I look at what it's doing focused on this tree, it's sort of jumping around the tree in some way. And it's not going to be kind of a continuous function on the tree because it can take, but it's somehow some process on a tree. So if I just focus on a tree itself, it's something jumping around the tree, and the way it jumps around the tree depends on what the dual tree looks like. Hey, it's not a continuous walk, but you know, just because it's not continuous, does that mean we have no hope of defining it? You know, maybe we can give a description of this thing with its strange jumps, and you know, there are plenty of discontinuous processes we can define. So maybe there's something to do there. I mean, you know, the gluing, certainly when you're gluing two independent random trees, the structure of the trees could not be simpler. So it's not like the underlying objects are complex. It's just figuring out how to describe what the walk is doing, we don't know how to make sense of. Another question is, what's the most natural formulation of a higher genus quantum surface, where now the conformal modulus is allowed to be random? So what's the right conjectural scaling limit, for example, of a random quadrangulation of a torus with n faces as n goes to infinity? So uniform random quadrangulations conditioned to have the topological type of a torus. There's some finite set of ways of doing that with n quadrilaterals. Choose one uniformly at random, maybe with a marked vertex or something. What's the scaling limit of that? I mean, I haven't really given you a way of defining this. I mean, you can take a torus and define a Gaussian free field on that, and that will give you, but then the conformal modulus is fixed because I started with the torus and put a free field on it. I want you to give me something random where the modulus structure is itself allowed to be random. Well, maybe. So you could first choose the distribution and then choose the free field. But remember, even choosing the free field, you know, if I choose a regular free field, I mean, how do I even define a free field on a torus? Well, you know, there's no boundary, so I have to normalize somehow. I can normalize by making the total average 0. But then the total average is not conformally invariant. You know, if I were doing this on a sphere, say, you could see that the average is not invariant under conformal automorphisms of the sphere. So, you know, in the sphere, for various reasons, I think this thing I constructed as this limit is the right notion of the quantum sphere of unit area. But I don't have a right notion of a quantum torus of unit area. And I don't even know, this is a question that Andrei Okunkov has been asking me for years. He's been asking me, can you at least prove for me that, answer for me whether when I take this torus, if I look at the that it's not the case that I just get a sphere with a really tiny handle on it. You might think of the scaling limit, just the handle becomes smaller, so that if you were to conformally map it to something looking like a regular torus, all your mass would be at one point. So even just show that that doesn't happen. Show that you have give a plausible argument for why that doesn't happen, for why you have a non-degenerate random measure on a torus in the end. So that's, I think, a fairly fundamental question. And it's something, you might be able to do it with conformal loop ensembles. And, if I take a conformal loop ensemble independently, then we know that the inside of a loop and the outside of the loop should be independent quantum surfaces that I'm just welding together. And maybe if I take two pairs of pants and weld them together, I can start creating a torus or a higher genus surface out of these. And there may be some way to construct what is the canonical random pair of pants with some conditional lengths on the boundaries. And I don't know. I'm not convinced it's impossible. You could find a way to stitch things together and somehow make sense of 8. But as it is, I've got nothing for you. So it's an open problem. Okay, next thing is, okay, well this is, maybe 9 is more of a musing than a question. But the musing is that there's a natural way to combine Liouville quantum gravity and AC geometry. And that's just to say, let H be a complex valued field, whereas real part is the Liouville quantum gravity part, and the imaginary part is the AC geometry. And then, when I use the transformation law, I would take Q minus I times chi times the log of phi prime, so that when I do a transformation, the real part, gets this Q log added to it, and the imaginary part gets this minus I chi log added to it. So both pieces transform the way they should. And I can, create both Q and chi out of the same kappa. And, okay, this gives me something. So right now this is nothing really other than cute. Just the fact that, the AC geometry somehow encodes the statistical physical model, the SLEs, all of that. And the Q part encodes the metric structure. So I can put them all together in one complex valued field. Okay, but so what? Well, I have a question is, what could happen if instead of taking Q minus I chi, you take some other complex number? Is there anything interesting that happens by taking this perspective? Okay, I say it's more of a musing than a question, but does looking at it this way get you anywhere? Okay, this next question, question 10, can you fully construct all the rays in the altimeter compass geometry, starting from all different points in D, and determine which rays intersect each other in themselves, and so forth? So this is something I at one point intended to do and never did, and would just be happy if someone would just do it. There's this puzzle of, we kind of know once an SLE gets started. By Julian's paper, we know once the flow line of the free field gets started, we know how to generate the rest of it. But if I take a point in the interior, how do I get started from that point? That we don't know how to get started from a point 0. And then once you get started, you want to show that, if I start from a different point, these are going to merge together, and you're going to get some tree. And you take some other point, you're going to get some dual tree. If you draw the flow lines corresponding to the opposite direction in the AC geometry. And the AC geometry is really, as a geometry, it's a fairly beautiful object. If you look at the triangles, the the sum of the edges in a triangle in the AC geometry, they always add up to 180 degrees. And it has a lot of things in common with Euclidean geometry. Two paths only cross each other at one point. I mean, it's a rather beautiful geometry, which it's not Euclidean, it's not non-Euclidean, it's sort of something else. And all of these nice properties, which are detailed in the appendix of this paper, should have nice analogs in the GFF setting. And okay, do it. Just actually make all of this work. And and it has to do with when a path crosses another path, it may continue to hit the path at different places. Some paths may wander around and hit themselves, or they don't cross themselves if gamma is too large. Funny things happen, and just making sure everything is well defined and paths do what they're supposed to do, it's work. Okay, so that's okay, and now finally I could say let's return to the original physics motivation. So at some point when this whole quantum gravity subject started, people were thinking about physics. Polyakov had some ideas. String theorists had some ideas. Okay, go back to the actual string theory and see what can we do. Can we add some of the complexities you would get in string theory? Can you add, for example, in some way figure out what these things mean mathematically? Take Liouville quantum gravity in a Minkowski space-time, maybe with complex weights instead of real ones, with supersymmetry. You have to figure out for yourself what that means. I'll put it here as a word. Can you put in the standard model gauge theories and build in an embedding of your string into a Calabi-Yau manifold? Okay, can you just add in all this extra decoration to the theory and make sense of it? Maybe you can just put a piece of it in there, but somehow, if string theory is really on its way to being a meaningful physical theory, and if these random surfaces, world sheets of strings, are somehow underlying it, maybe you could add all this. And something I didn't add here is you should also add this random conformal moduli. Supposedly in string theory, it matters you can integrate over surfaces that aren't simply connected. So you have to somehow put that in. And well, okay. I don't know. Did you want to say something, Bertrand? Yeah. Okay. What's that? Yeah. So it's fairly ambitious, but try to make sense of just at least one thing. Try to add one piece of complexity to the model. I think, can you somehow make sense of Polyakov's original motivation for Liouville quantum gravity? He was talking about the time evolutions of flux lines of gauge theories. Okay, what was he talking about? He always said there was some sort of duality between these gauge theories and these flux lines, which would just be simple paths. And that somehow understanding what these lines do should tell you what the whole theory does. Can you make any sense out of his idea? He himself wrote in this memoir, but he still hasn't made sense of the idea to his satisfaction. So it's not something that physicists really understand yet, but that was the original motivation for getting this whole subject launched. So go back and take a look at it. Another thing, can anything be said about higher dimensional random metrics? So if instead of 2 dimensions, you take higher dimensions. So Bertrand tells me these appear in what they call loop quantum gravity, various models for trying to have an alternative to string theory for constructing a quantum space-time. But just, come up with something, glue together tetrahedra in some random fashion. Or, use some other random field. Can you come up with some natural higher dimensional random metric? You don't have the Riemann mapping theorem or Riemann uniformization at your disposal, unfortunately. So that makes the whole story much harder. We don't really know how to get started in that case, but do something. Well, take e to the gamma times the Gaussian free field. I mean, this will be something very special because it's conformally equivalent to the plane, to R3, whereas most geometries are not conformally equivalent to R3. But you might want a random geometry where, conditioned on the conformal class, you have a Gaussian free field in there. That's something you could conceivably ask for. And then another question is, can you give a 3 or 4 dimensional version of the AC geometry? And in this case, we have a guess because Gatti-Cosma's result tells us that the uniform spanning tree in 3 dimensions has a scaling limit, rotationally invariant scaling limit. And this gives us some set of flow lines. And you might try to understand the continuum object, construct some continuum collection of lines. And if you could really do this, you might be on your way to making sense of these gauge theories, this $1 million Yang-Mills problem, all these puzzles that really boil down to understanding random geometries, random connections in higher dimensions. So if you can just take one thing that we learn in the lower dimensional case and however crudely find some way to extend that piece of knowledge to a higher dimension, then that would be a breakthrough. Okay, so it happens I've spent a lot of time on open problems and have not left much time for the welding proof. But personally, I think that's actually for the best. Because I really think that these open problems are important to get out there, because that's where the future is, that's where it's going, that's what if people in this room want to get started on this subject, these are things that one can start thinking about. And maybe just to say in 3 sentences how you prove the conformal welding. Essentially, you just show if you take this capacity invariant thing and you weight by the amount of mass passing through on the left, and you weight by the amount of mass passing through on the right, those 2 things give you the same measure. So, if I give you something that's invariant with respect to one time, and then I weight by the amount of stuff going through in this other time, that gives me something that's invariant in the other time. And I just kind of, by approximations, I construct the weighting on the 2 sides separately and show that you get the same thing. So the 2 sides have to be the same. Okay, so it's an argument that you kind of have to step through carefully, and it's it's in the paper, and I'll be maybe adding some more details to it in the next few days. But it's very straightforward compared to this list of open problems I've showed you. And you want to focus your minds on the big challenges. Okay, so that's all I have.